right, so here we come to an example slide. First one really in this entire chapter, since everything up until this point we've been working together. So I would like you guys to take kind of a break to decompress and digest what we've been talking about. Draw the resonance structure for the polyatomic ion of carbon, or of carbonate. In addition, I would like you then to calculate the bonding order of the molecule on top of that. So please pause the video, approach this problem now. All right, hello and welcome back from the pause. So we are going to approach this together, just compare our work, see if you were able to do this correctly by following my steps as well. So we're going to start by counting up the total number of valence electrons that we are working with in the carbonate polyatomic ion. So we're going to pay attention to our carbon first, then oxygen, and have to take into account this -2 charge. So our carbon has a total of 4 valence electrons. There are 3 oxygens total, each of which has 6 valence electrons around it. And because of this -2 charge, we have 2 extra electrons, right? The 2 additional electrons give negative charge. And so if we take 4, add it to 16 plus 2, this gives us a total of 24 valence electrons that we're going to have to place in and around this carbonate anion. So we're going to start with our element that has the highest bonding capacity in the middle. That's going to be carbon with a bonding capacity of 4. Carbon in the middle, and we're going to place our 3 oxygens around it. Oxygen, oxygen, oxygen. The total number of electrons that we have placed so far is equal to 2, 4, and 6. So we're going to subtract out 6 electrons from our pool thus far, giving us 18 electrons that we are still working with. So we're going to take these 18 electrons per our previously discussed rules and place them around the terminal atoms first. These count as the oxygens. So 2, 4, 6, 8, 10, 12, 14, 16, 18 total electrons placed, minus 18 electrons, and we have none left over. Because there are no valence electrons left over in our pool, we're just going to have to double check at this point and see if all of our atoms are satisfied. Each of the oxygens should be, since there are 2, 4, 6, 8 electrons around each of them. And if we turn our attention to the central carbon, we can see sadly there are only 2, 4, 6 electrons. So our carbon in the middle is not feeling too good. We need one more pair of electrons around it to satisfy its octet. Now we can see that there are plenty of locations to pick a lone pair from. We could either pick one lone pair from the oxygen up top, one lone pair from the oxygen on the right, or one lone pair from the oxygen on the left, but we can only pick one, right? We can't add too many electrons to carbon. That's also going to make it unhappy. We need 8 electrons to satisfy the octet. So this is where the resonance structures are going to come in to play. We need 3 different structures to represent these 3 different options and the corresponding resulting Lewis structure. So if we pick our lone pair from the top, our structure is going to look a little something like this, with a double bond between the oxygen and the carbon up on top, and all of the rest of the oxygens still having their lone pairs intact. If we picked it or if we pick the double bond from the oxygen on the right, we'd have a single bond to the oxygen up on top this time. The double bond would be on the right. All other lone pairs still intact. Or if we picked the double bond from the oxygen on the left, again, single bond to the oxygen up on top, single bond to the oxygen on right, double bond now present on the left. We've pulled one of the lone pairs in from the oxygen on the left, and all of the other lone pairs are still present. So here we have 3 different options for where the lone pair can be present, and in reality, just like the ozone case, we don't actually end up experimentally seeing 1 shorter bond distance and 2 longer bond distances. We actually see each of these 3 bonds being exactly the same. So what this tells us is that these structures that we have illustrated are in resonance with each other, that the double bond is actually just kind of rotating around the molecule as the electrons dynamically fluctuate. Oh, and before I forget, the last thing we're actually missing on this structure, because this is a polyatomic ion, is to make sure, just as there is a -2 charge on the chemical formula, we have to have a -2 charge on our structure as well. All right, so in combination then, these three structures are the three resonance structures for the carbonate ion. The real structure, how this actually looks, is going to be somewhere in between these, with a bonding order not that of a single bond or a double bond, but somewhere in between that as the bonds all kind of fluctuate around. Our bonding order for the carbonate ion, we can see that we have 1, 2, 3, 4 different bonds present, and 1, 2, 3 locations where the bonds actually are, right? 3 different central points between the atoms where the bonds can exist. This means that our carbonate anion does not contain individual single and double bonds, but rather each bond is identical with a magnitude of around 1 1/3. So the bonding strength is going to be greater than that of a single bond, but less than that of a double bond. And similarly, the bonding distance is going to be shorter than a single, but still longer than a double. We're somewhere around 1 1/3.